ladies and gentlemen. I hope this day has been great so far and that you've been enjoying the summit. Also, the lunch break, I hope the food was good and you met some new faces, maybe caught up with old faces. So it's really great that you made your way back here. We're going to start with another session within the Intelligent Health track. We're here to focus on advancing pivotal conversations on AI and medicine and fostering global collaboration across the healthcare sector. Just to introduce myself quickly, my name is Ahmed. I'm a PhD student in AI and low resource language models at the University of Cambridge, and I'm trying to make AI more equitable and more accessible to everyone, so that also includes healthcare. But yeah, so now we're going to start with the next session, which is the presentation called AI Innovation in Healthcare at Weill Cornell, Qatar. Here to tell us more, please give a warm welcome to Ahmed Serag, Professor and Director at the AI Innovation Lab at Weill Cornell Medicine. Thank
you. Good afternoon, everyone. Thanks for coming. I believe we're missing still some of the audience. Probably they're busy with lunch, but we're going to start. I'm going to talk today about AI innovations in healthcare over the next 20 minutes or so, with a bit of focus on generative AI advancement that we have built here at Weill Cornell AI Innovation Lab in Qatar. Just to give you a little bit brief about myself, I've been in this domain with my background as a computer scientist for over the past 20 years or so across academia and industry. As you can see, that I've worked in developing and commercializing a number of technologies at Novartis, Philips, and also across academia. And today I'm going to speak to you about some of these interesting solutions we have built, but also again the latest generative AI advancements that we've built here. I moved to Qatar almost 1.5 years ago at Weill Cornell Medicine, and if you're not familiar with the institute, it was built as a partnership between Qatar Foundation and Cornell University from New York at around 23 years ago. And really this was because we wanted to push here excellence for teaching, research, and innovations in healthcare. I tried to speak to you today about many of the applications that we have seen over the past decade or so in medicine and healthcare. I tried to sort them up here from the bottom up. Not the bottom is the least valuable, but probably the bottom application probably the easiest. And we have seen probably huge advancements in these when we have AI applications for enhancing data acquisition. And when we move up to the next level, there's another type of algorithms where we can build to quantify and interpret data, right? And if we speak to a pathologist or a geologist to interpret some data, they might tell you why they're doing it, but maybe it wouldn't make the best logical argument to you. This is because it's based on knowledge that they have accumulated over years and years. So it's purely a perceptual task. Moving to the highest level, and probably the most interesting and has the big impact, is when we build AI algorithms for detection and prediction of disease. Having a diagnosis made by an AI algorithm is very important, but also very risky, because we want to understand the reason why these algorithms made that decision. We all know that AI data is very diverse, huge, and if we speak about one of the most complex type of medical data is imaging. As you can see, it's a very large portfolio. You can think of 2D images, 3D images, X-ray, MRIs, but also we now have access to histopathology images where we have the luxury now to look at millions of, if not billions of cells on a very large screen and being able to do a very thorough analysis of that. So let's start by seeing some of these applications and advancements that were built over the past few years before moving forward. With magnetic resonance imaging, we have managed to see the human brain in scale and detail that we haven't seen before. And as you can see, we learned more about the brain. We can see that it develops a lot within the first few years of life. Even if we have even a window, as you can see here, it didn't seem like the image was working, but when we look around birth, as we can see here also with a neonatal brain, we can see the brain, but there's lots of other complexities we have. There's motion. right? And what this means, when we try to image the brain, it's a 3D volume. So we try to do it actually by having a view from 3 different axes. But this leads to a motion corrupted image, as you can see here. So this would actually hinder our analysis and interpretation of data. By using AI, specifically machine learning techniques, we can build some algorithm that allows to automatically detect where's the brain, and this is very large field of view, and also detect some anatomical landmarks that will allow us actually to take these brains and ingest them together in a way that we can extract the 3D brain volume in a very high resolution that allow us to be able to have a true analysis of these data. By doing that, we managed to look at the brain and build some normative models of brain development that allow us to see how the brain changes in this short period around birth, and being able to use these models to identify if a newborn is having an abnormality or not. This early detection allows us to understand what's going wrong with the newborn brain and allows for intervention and provide therapeutics if needed. Also, we can extend these models across the lifespan, and as you can see, this provides us now with the opportunity that we can relate or track back a disease that a person gets in adulthood to what happened in earlier point of life, but even we can go back and track this from birth. As you can see, there have been a huge number of applications in imaging. As you can see, we talked about radiology, there's also pathology and ophthalmology and so on, but it's clear that radiology probably has the most advancement and impact of AI. This is because probably radiology is digital by nature. If we think about pathology, there's a huge opportunity for AI in pathology, but we know that pathologists have been trained to look at the tissue samples under the microscope. In the early 2000s, we started to have scanners where we can put the glass slides and be able to look at the digitized image, very large field of view with magnification that can go up to 40x. By doing this, we can analyze, share the data with colleagues, but also being able to have this through analysis that could go to the level of each individual cell. Once we digitize the images, there's of course opportunity for AI. Very sophisticated pipeline you can see here based on deep learning that was built for diagnostic pathology. It's not one neural network, it's a cascaded multi-resolution neural networks where each network here in the system has a specific function. At the lowest resolution, the top, is a neural network that actually looks at a very high level, detecting the tissue and excluding artifacts. This means these artifacts cannot mislead our algorithm and will be able to find the region of interest very precisely. In the mid-resolution level, there's another network that goes and finds the tumor area within this piece of tissue. And on the highest resolution level, we can go and identify each individual cell and being able to classify this as tumor or non-tumor. By fusing the decision that comes out of these different networks, we can actually now have boundaries for the tumor region and being able to classify each individual cell. This has been commercialized actually through Philips for molecular pathology and has been applied for multiple organs and multiple cancer types, as you can see. But what has been very interesting is even when we look at the individual cell and the cellular assessment, when we quantify and classify this cell, the algorithm has been doing outstanding job, very close to the human expert. There have been also AI applications of ophthalmology. We have seen that we can use retinal fundus imaging and do vessel segmentation, and the algorithm have been coming quite close again, but even slightly sometimes outperforming the human expert. Another modality of ophthalmology when we look at optical coherent tomography, and this allows us to look at the thickness of each layer of the retina that allowed us actually to personalize the goals for the patient based on this information that we derive from this imaging modality. You can see here an example of molecular degeneration. This age-related molecular degeneration is actually when people lose vision over age. But now we can identify at what stage they are and being able to give them the right dose at the right time. We can see also another modality, corneal confocal microscopy, that has pioneered by Professor Malik from Weill Cornell here in Qatar. And we now recently got a grant from Qatar Research Foundation, where we can actually now look at this corneal confocal microscopy, which shows you these lines are the nerves within the eye. And by looking at this and analyzing them, we can see if these nerve damages could be related to one of these peripheral neuropathy diseases. As you can see, the pattern looks very, very similar. It's very difficult for an expert to be able to do that. This is the work that we just started. It's not complete yet, but I was excited to show this work that has been done by our postdoc in the team, Dr. Shaima bin Rabah, that showed that actually AI can provide very high accuracy of diagnosis that could actually reach, for some of the diseases, almost perfect, 100% detection. Moving forward to generative AI, we started all to hear this term a lot, but actually it started probably with the hype of language models and the likes of ChatGPT a few years back. And most of us might think generative AI, ChatGPT. But ChatGPT is not only the generative AI tool and vice versa. Having this timeline here, you can see that at the late 90s, we started this idea of the generative AI. But the two pieces that I could really identify, one happened 10 years ago, was Ingrid Fellow and colleagues built what we call generative adversarial networks. Two networks that actually could be used, as we have seen previously, transform the style of a group of images to look similar to other group of images. And after that, the second peak happened in 2017 with the paper from Google when they built this attention all what you need. The transformer architecture that ChatGPT, but 99.9% of all the language models we have now are built on. I can see myself there are three main dimensions when we apply generative AI in medicine and healthcare. And this is largely defined by the type of data we have. So if we think of the data that comes from the imaging, and this falls under the vision group, there's this other type of data that comes from electronic health records or text or tabular data, and this is probably the language. And the other and the most important is the multimodal, when we see integration of vision language, but probably also could be other modalities if we have access to. This opens the opportunities for very innovative applications, as you can see here, privacy preserving, decision making, but the most interesting again is the medical report generation with the integration of these types of modalities. We've been speaking in the panel before lunch about data access, how it's difficult. It seems like everyone work in healthcare, which is a regulated area, as we know, having difficulty accessing data. And a recent report that showed that we have around 20% of the data at healthcare organizations or hospitals usable for AI. This could be due to a number of challenges, could be due to data heterogeneity. This data has been acquired by different devices made by different manufacturers. Data imbalance, we know in real world data is not ever balanced. And also the data quality, I will show some example of the fatal imaging and how the data could sometimes be in not the best quality. We have worked on algorithms to solve these solutions. And again, some people talked about federated learning that allows you to build AI models without sharing the data. But another approach is actually by building synthetic data that could be shared when you have the patient data be identified, and this means like to preserve the patient information, there's nothing to worry about. But the major problem here is that how you make sure that this data you generate still captures the statistical and clinical biomarkers or hidden information that the clinicians need when they do their diagnosis. Because when you similar techniques in deepfake, you can look like roughly on the two images and say, yeah, these two persons look alike, but it's different when we talk about this in healthcare. We built this solution here based on state-of-the-art denoising diffusion models that allowed us to generate this synthetic data, and we can use it to train the model. Now I'm going to give you literally 10 seconds. One of these data is not real. Just in your head, choose if it's going to be C1, B2, okay, and then I'm going to show you the result to see if you can make it or not. Okay? If you made a choice, you're absolutely wrong because all of this data is fake. And the right-hand side is actually all the real data. And you can see this technique that we have built have been applied successfully on a number of modalities, including radiology, ophthalmology, and pathology. It's very difficult to distinguish, but we have made other tests that will go soon into our publication that show that this data we generated actually captured this clinical properties that we're interested in. Another important application, how we use generative AI, specifically language models, for example, for decision making. We use it a lot for text generation, you chat to models like ChatGPT, but can these models make a decision? And the most important, its ability to generate not just any text, but to generate the reasoning, why the decision was made. And our application of that is to look at intensive care units in hospitals. We know it's one of the most expensive units in hospital, and it has the most expensive equipment, and the patients that go there are probably in very serious stages. The biggest problem after that is that some people leave, and after a while they go back. So we call this unplanned admission. So this unplanned readmission actually puts additional pressure on the healthcare systems and also escalate the cost and the utilization of the resources. So here in this work that has been led by Huda Helmi, a team member, she built a language model that would have access to electronic health record and being able to take data of each patient as age, patient history, and any other information that we can find in the electronic health record of the patient to train the model to be able to answer this specific question. Like, this patient is likely to get readmitted to the ICU or not, and why. This example of the responses we got, it has been doing pretty well, telling us if the patient is likely to get readmitted or not, but as you can see, it's giving you also that information. That's a brief demo. I hope it's gonna work to show you. Okay. So you can see you can enter the patient. This early stage demo, but you can see you can enter the detail of one patient, and then the model will tell you the response. Moving, because I think I'm running out of time, to the multimodal and the most interesting, medical report generation. Clinical reports, either coming from radiology, pathology, are very important. But we know there's a lot of challenges associated, either from the overwhelming workloads, and even we know there's shortages in pathologists nowadays as well. Diagnostic errors, time constraints, and so on. So how AI can help with that? By bringing these different modalities together, we can build AI to interpret these images and write the reports automatically for the doctors or the expert to just approve instead of spending hours on the reports. If you're familiar with MICAI is a medical AI conference, very prestigious one that came with this challenge this year, where they have a number of CT images of different organs, as you can see. And the whole challenge was about using state-of-the-art generative AI to generate automatically reports for these. We have built a lab with the two team members, Ahmed Ibrahim and Abdullah Husseini. This method here, as you can see in Breaker, I won't get into details, where you can encode the images using a specific encoder trained on 3D medical images, which adds, you can think adds a very high complexity. These are not 2D images, we're just showing your slides, but actually 3D. And we have a text input here that gets encoded as well, and we're sending these two encoded features to a large language model to be able to generate these reports. We have got very good results out of that, and actually the team got a special award at the time. I have to tell you, like, the Ahmed and Abdullah actually are two persons with bachelor, have been competing with postdocs. They have done a brilliant work here. And also I'm gonna show you now a demo of this system. Very early stage, but as you can see, you can load a CT scan. I'm asking a simple question, kind of describe what you see on this CT scan. And in literally a few seconds, instead of hours that could be spent by the experts, you're getting this short summary written for you about what the model can see in the images. Just to conclude, generative AI systems are great, but they don't really reason or plan. comes with the nature of these models built with these transformers that are very excellent at doing this pre-text prediction. But we have, if you play with this ChatGPT Gemini, you'll see a lot that gets a lot of errors in math and a lot of this reasoning thinking. So the other issue that these models in general needs an amount that is huge, millions of data samples to be able to do a simple task. But actually humans, if you get, as I always say, a 1-year-old child and give it once an example of a cat or a dog, they will be able to do this brilliantly without thousands of examples that we need now for these models to train. A few years back, Jeff Hinton, as you can see, one of the godfathers of AI, came up with his code radiologists will be obsolete in 5 years. We can see now we're in 2024. We don't have the claim of Jeff Hinton, but also we don't have the claim of Elon Musk. We're still having radiologists driving regular cars going to work. This will change, but what I want to say is probably this wouldn't happen in the next few years. Before anything, I want to thank the team that has been doing this incredible work. Very talented people, as you can see. We have a spectrum of postdocs. They're all technical, really, computer science, bachelor, masters, you can name it. Medical students as well that have been trained and working closely with them to be able to understand what is AI and how to utilize it and understand it when they later go and be clinical professionals. We have started great collaborations locally, as you can see, but also globally. For a lab that is 1.5 years ago, we're very proud of what we achieved, and I would like to thank you so much for your attention, and I'm happy and glad to connect with you and discuss if you have questions or you're interested in collaboration. Thank you.
Thank you so much. That was really great. We actually have some time for a bit of a Q&A, if that's all right with you. Perfect. So, if you have a question, please raise your hand, and then we'll have someone with a microphone coming up. Just checking. We all have, okay, there's a question. We need a microphone. Wait, there, perfect, okay. Please raise your hands again so we can get the microphones. Okay, here in the first row. Thank you. Yeah.
Hello. So, hello Dr. Serag, my name is Ahmed. I am founder of a stealth startup called Progress AI. We are trying to do some inferencing stuff in the EMR. I got pretty interested in one of the slides you had that you had these 3D images, like the DICOM files, and you're trying to create a 3D encoders. So the question is like, did you guys come up with the whole algorithm to create 3D encoders? Encoders for features for those DICOM files, or like are you using some pre-existing ones to encode and to extract features out of them?
Are you talking about the medical report generation?
Yeah.
I think for the image encoder, we were relying on pre-trained one, but for the things, honestly, both of them might have been pre-trained. Honestly, also we explored other alternatives of pre-training our small algorithms to do that. I think this might be showing up in our publication, but we just want to maybe for this challenge specifically because of the time constraint, we relied on pre-trained model either for the imaging or for the language.
Just a follow-up quick question. Are these available on GitHub somewhere that we can take it off?
Hopefully soon. As I said, that's a sneak peek, but hopefully once it's published, everything will be accessible.
Awesome. Thank you.
Thank you. Okay, let's go over to the, okay. You're going to pass it on. Thank you.
Just wanted to ask about, for your report generation, so these are outputs that radiologists would write as a radiologist kind of in the clinical background. So they would write. How much have you included radiologists and other clinicians in the development of your algorithms? How much human in the loop do you have in this? And is there a verification afterwards of the actual accuracy of it?
That's a good question. For this data specifically, as I said, that was a grand challenge. So all of the data that was there for the challenge images and the associated reports has been provided as they are. Probably, as I said, they have been reviewed initially by the experts, but we had to just compare against the ground truth that was there, right? So it is very large, it's hundred thousands of images and associated reports, really. And I think testing these in the real world, even different data sets, will be the next step and will be probably the real challenge.
Okay, thank you. Oh, yes.
Thank you for a great presentation. You had a slide up, I think earlier in the presentation about, I think, different FDA approvals over the last 5 or 6 years. And there's a large cluster in radiology, et cetera. From your perspective, I don't know if they can put that slide up yet, but I don't know, from your perspective, do you see any trends as to most of the innovation will stay in the radiology area, or will it go to the other clinical areas? Do you see anything from your vantage point?
I think there have been a huge shift over the past few years. So, as I said, it was probably easier for radiology because the images were digitized by nature. You get the CT scan and MRI were all digital. So it made it easy to build algorithms to do that. But as probably, if you're following, you can see a huge number of startups and companies now focusing on digital pathology. Because now there's access to this large number of whole slide images. And it actually is more challenging than the radiology. For me, it's a whole world, very large, and every cell counts. How you identify this cell, classify it right, and making up to the decision based on this group of these small cells together to say at the end, this patient is, for example, at grade 7 of prostate cancer or not. That's a challenge. I think that's why probably, I would say in the past 5 to 7 years, people have been shifting the focus a little bit to pathology. And we can see also now with ophthalmology. And I think people started to trust more AI now, and related to a similar point when people said about the adoption and if clinicians accept that or not, I think there's no way out. They will have to do it. I dealt with pathologists myself, and they will say, I hate to look at the screen, I was trained to look at the microscope. But when they see the opportunities that this algorithm gives them, that are much, much more than what you see just under the microscope, they likely accept that and be glad to do that.
Here I know, a quick follow-up here, I know you've been doing a lot of, you and your colleagues have been doing a lot of academic-based research, et cetera. To what extent do you see commercialization of these digital AI technologies progress through the pipeline domestically here? How has that been?
I talk in general, or you want to talk about the region, or?
Well, I'd say, since we're kind of, let's talk about the region. I guess I'm just trying to see, in different parts of the world, there's a lot of academic interest, obviously, but you can see in different parts of the world, due to various reasons, commercialization is quicker in one part versus the other. To see if you had any thoughts about that in this region.
So just in brief, I've overseen the commercialization of the likes of the digital technology. I think you have two tracks. When you think of commercializing research purpose only applications, that's the easiest part, right? Because you don't take really much responsibility. I think the responsibility and the complexity lies when you want to say, I'm now building or commercializing this for clinical applications. And this is the issue. Now, give you a brief also difference about doing this, assuming you're building this, let's say, in academia, and then want to translate that and commercialize it, or do it in industry. In the industry, it's much easier. Access to diverse data from multiple centers to multiple data experts on get your data and validate it. I remember at this time we had thousands of data that we could get in Philips. In academia, you don't have that. And this is huge because when you want to deploy this, right, because this is the bottleneck, you build things, either it goes to a product or goes to publication, etc. The bottleneck is validation. You need diverse data from multiple centers rated by multiple experts, right? And being tested really in real world setting. And I think this is the struggle. I wouldn't say only here in the region, but probably in the whole world. We're definitely lagging behind here a little bit, but this is really the bottleneck that if you want to move to commercialization, validation is key.
Thank you. Okay, and that's about all we have for the Q&A now. Thank you so much. That was really great. And now we're going to go on to the next speaker. Thank you.